Everyone. I'm very happy to see so many people on Wednesday. So usually our webinar is on Tuesday, but we have this great opportunity to welcome Professor Michael Weinstein, who is a prominent mathematician working at Columbia University. And today, Michael is going to talk about dynamics of waves in continuum honeycomb structures, so topological crystals, if you wish. Professor Weinstein.
Okay. Thank you, Sebastian, and thank you for all the organizers for this opportunity to speak. So I'll be giving an overview of work over the last number of years on dynamics and honeycomb structures. And I have quite a number of collaborations in this field. The work began with Charlie Pfefferman, and I'll be talking about work that touches on what Alexis Drouot did when he was a postdoc at Columbia. Maxence Cassier also was at Columbia, and we continue our work. James Lee Thorpe was a student of mine, and I'll be mentioning some recent work with Jacob Shapiro on magnetic systems. And then there's a collaboration with physicists at Penn State University, Mikhail Rexman and Jonathan Guglielmo. So the topic is wave phenomena in novel crystalline media. Mostly periodic, although I will say something about methods that apply to disordered media as well. So, but the motivation comes from two important developments at the intersection of wave physics, material science, and mathematics. So the two developments, I would say, are the discovery and controlled fabrication of two-dimensional materials, the paradigm of which is graphene, single atomic layer of carbon atoms, shown here, arranged in regular hexagons. Each vertex of the honeycomb has a carbon atom. And then there's an interplay between topology and wave equations, or in particular topology and PDEs and other models like tight binding models, discrete models, homogenized models. And this interplay leads to explanation of the remarkably rich wave phenomena that one sees in graphene, but not just graphene, but graphene when you break symmetries, like you introduce a magnetic field which breaks time reversal symmetry, or you make deformations, mechanical deformations of graphene, and related materials. And this interplay of topology and wave equations really finds its origin in the discovery of the integer quantum Hall effect, which is a phenomena that arises in 2D when you introduce a perpendicular magnetic field, which induces currents which move around the boundary of the sample, and these currents just continue to do that. And do so in a very, very robust way, even if you introduce localized imperfections, localized even large imperfections. It was Thouless probably I guess in the late 70s and 80s and collaborators who recognized that this so-called quantized current is related to the mathematical formulation, and was able to derive topological indices to explain it. I'll say more about that. But there's been a recognition that a lot of the key phenomena in condensed matter physics setting actually really just depend on symmetries and spectral properties of the underlying models. So we could be talking about wave equations and acoustics and electromagnetics, elasticity. And just as long as you have wave equations with certain symmetries, periodic structures with symmetries, then you can see a lot of these effects. And even it turns out that when you deform these structures away from their symmetric situations, they still persist, even in situations where you don't have block waves. So recognizing that it really was about the models, or about phenomena which have a common mathematical structure, this has inspired experimentation with artificial variants of graphene and other materials. So I'll give some examples. There are many, many examples now. I'll first introduce some terminology. So I'll refer to bulk structures. So these are infinite periodic structures, infinite perfectly periodic structures with no defects in them. And then we'll talk about edges or interfaces. So these are line defects. And if you think in terms of the operators that describe them, these are non-compact perturbations. So they're not localized distortions of the media, but rather they really are huge in perturbations in an operator theoretic sense. So for example, there are sharp terminations. So these are both, if I look in the middle here, then this is bulk graphene here and here, but then I could terminate it in various ways along an armchair edge or here along a zigzag edge. Another kind of deformation or introduction of line defects are so-called domain walls. And a domain wall amounts to taking a structure, and maybe you have the honeycomb structure, and what you do is you compress it on one side of a line and stretch it on the other side. Another variant would be the honeycomb structure is a structure with 2 atoms per unit cell, often labeled A and B. So if I make the A atoms have higher contrast than the B atoms on one side, and then the other way around on the other side, that would be an example of a domain wall as well. And so and what are edge states? Well, these are interfaces, and very often one has concentration of energy along interfaces and many fields of physics, and edge states are going to be eigensolutions. They'll be solutions of a spectral problem with the property that they look plane wave-like in the direction parallel to the edge, and they're exponentially localized perpendicular to it. So that, so here the edges, the edge states look like that. Let me draw it over here. It will turn out that for sharp terminations of the graphene structure, the zigzag structure supports edge states which propagate along the edge, whereas in the armchair case it doesn't. One of the goals is to understand things like what role does orientation of the edge play in concentration of energy. And this is a cartoon of an edge state. Propagation in this direction and exponential localization transverse. Okay, so now the examples. So the first example to mention of artificial graphene is the work of Haldane and Ragu. They wrote a theory paper, a couple of theory papers in around 2006, where they proposed an electromagnetic variant of the integer quantum Hall edge states. Okay, so remember there you had this perpendicular magnetic field and edge currents running around the sample. And what they did here is they proposed it in what are called gyromagnetic media. And it was an experiment was done quickly after the paper by the group of Marin Solyachik at MIT, where, and this is a numerical simulation. You have 2 media. Basically, the media here on top is just enforcing a kind of boundary condition at its edge, and the structure here has some kind of spectral degeneracy, like not a Dirac point actually in this situation, but it has the same qualitative effect. Where here's a point source, and point source generates solutions to Maxwell's wave equation, and the waves propagate in one direction. The waves are propagating unidirectionally because it's a gyromagnetic media, so it breaks time reversal symmetry. Waves propagate, and even if you insert a very large local perturbation, the waves just circumvent the barrier and go around without substantial scatter into the bulk. And no backscatter because there's no backward channel for propagation. So you see unidirectional edge currents, and these are very robust, even in the presence of a very large but local perturbation. Now, I'm not going to say much about topology in this talk, but I just want to mention that, well, So this was, the theory work and the experiments were inspired by the field of topological insulators, of which this phenomena of unidirectional edge currents is a hallmark. Very roughly, a topological insulator is a material which in a certain range of energies or frequencies, if you're thinking in terms of electromagnetics, it's insulating in its bulk form. If you look at the infinite structure, it's insulating. But then when you introduce a boundary by, say, cleaving it and abruptly terminating the structure, it has conducting states along the boundaries. Okay. Furthermore, where's the topology? Well, this phenomena is quantified by topological indices. And since, if you buy that, then since topological indices are stable against localized deformations, then the phenomena is stable against imperfection. So that's sort of the overview of what a topological insulator is. Now, how do you go from, say, PDEs to topological indices? Well, just consider a media which is described by a PDE with periodic coefficients. Then there's a Floquet block band structure. And then associated with the band structure, of course, are projection operators, which you build out of the Floquet block modes. So there are these, I want to project onto a particular band. In condensed matter physics, what one constructs is Fermi projectors, and those are given in terms of the Floquet block theory. And out of those Fermi projectors, one can build operators called Fredholm operators. Okay, certain Fredholm operators, and the index of a Fredholm operator is an integer just by construction. It's the dimension of the kernel minus the dimension of the co-kernel of the operator that you're talking about. So by construction, it's an integer. In 2D, for 2D media, this Fredholm index can be rewritten in terms of the Floquet block modes as an integral of the Berry curvature over the Brillouin zone, the torus. And that's an expression for a Chern number, which is an integer. In the context of the integer quantum Hall effect that I mentioned, this index is actually, you can rewrite it as a physical quantity, the quantum Hall conductance, which is physically measurable. So it was actually, it was Thouless and company who made this observation that you can take the quantized Hall conductance, which comes from something called the Kubo formula in condensed matter physics, and you can rewrite it as a Chern number. And so that's just a summary of where the connection with topology comes from. Now, other examples. So I'll give a couple of others. So in photonics, there's work on periodic media. So what you do is you take optical waveguides and you arrange them so that these optical waveguides, which are going into the screen, have a honeycomb arrangement. Their cross sections are honeycombs, and then what is done is one coils these optical fibers, these optical waveguides. That coiling introduces a kind of break of time reversal symmetry. The governing model in their setting is the paraxial approximation for the wave equation, and so what one gets effectively is a Schrödinger equation. In the linear regime, it's just a linear Schrödinger equation with a periodically forced honeycomb structure. And here are the edge states which propagate around edges of an array. You don't see the array very clearly here, but you do see the concentration of energy which moves along the edge. If the edge, if these states were not robust due to some topological explanation, the energy would just spread, scatter into the interior of the array. Another example is honeycomb arrays of gyroscopes by the group of William Irvine, and there you have a coupled mechanical system. It's magnetic. These gyroscopes have a direction of spinning, and direction makes the system chiral, and one has nice propagating edge modes. Even if you remove some of the gyroscopes and introduce imperfections, things might scatter a little bit around, but then notice how things reorganize and the waves propagate around the boundary. Okay, so so the outline will be, I'll first talk about the mathematics of the bulk. I'll define Dirac points and talk about the roles of parity inversion symmetry and time reversal symmetry. Then I'll talk about the mathematical problem of interface or edge states along line defects of the type that I mentioned. In particular, we'll talk about sharp terminations, domain walls, and then this question of this deformation by a non-uniform strain, which leads to an effect called pseudomagnetic fields and Landau levels. And then connecting to what I just said about topology, when time reversal symmetry is broken, say, by a magnetic field, then these edge states that we talk about are stable against arbitrarily large but local perturbations. Okay. So continuum wave equations. So these are going to be the sort of the three models that come up in this talk. First, just the single electron model, non-interacting electrons in a two-dimensional media with a periodic potential. There's also the magnetic problem where you have a vector potential whose curl is a constant vector perpendicular to the plane. So that's a magnetic electron moving in a crystal in the presence of a perpendicular magnetic field. This is the basic model of the integer quantum Hall effect. And then TM and TE electromagnetic waves. This covers both cases in 2D. Comments about general crystalline media. So we have a periodic potential. In the plane, there's a period lattice, which is all integer linear combinations of two independent vectors. There's the dual lattice, and they satisfy these standard relations. Here is the honeycomb structure, which is actually the union of two lattices. These are two triangular lattices starting at an A point and a B point. So we have two lattices here. The triangular lattice has as its dual lattice as a dual lattice, which is also triangular, and the fundamental cell is called the Brouin zone. So we'll in the case of a triangular lattice, it's a hexagon. Square lattice, it would be a square. So we'll do a lot with these examples. Okay. There is block theory, Floquet block theory, which so you have, what I want to emphasize is if I look at the Schrödinger evolution, in the case of the Schrödinger equation, we propagate initial conditions, then we're able to write the solution as a superposition over all of the Bloch modes. The phi b's are generalizations of the plane waves, and this projection onto the phi b's are just a generalization of the Fourier transform. And the EBs are dispersion relations. They play the role of E of k equals k squared for the free Schrödinger equation. So more specifically, EB of k and phi b of k are eigenpairs of the Floquet-Bloch eigenvalue problem in a space which I call L2k. L2k just refers to this pseudo-periodic boundary condition. So, so if I think about the operator H is this operator here without specification of boundary conditions, but if I look at it in the space L2k, if I look at it on functions which satisfy that boundary condition, I denote that by HK. And I can say I can obtain all information about the operator H acting on L2 by studying the individual operators and then summing them up appropriately, integrating, forming continuum superpositions. That's what this symbol means. So for each k in the Brouin zone, this operator has compact resolve, and so HK has compact resolve, and it has a discrete spectrum, which I write in like this, ordered real numbers because of self-adjointness, and they're listed with multiplicity. And these eigenvalues, as they vary with k, are called dispersion relations, and their graphs are dispersion surfaces, and these are Lipschitz continuous maps, Lipschitz continuous surfaces. Nothing worse than a conical singularity, it turns out, and that's deeply connected with self-adjointness. And there's the band structure. Well, the band structure refers to the totality of these mappings and their corresponding eigenfunctions. Again, the EBs are at best Lipschitz continuous, and the phi Bs are not even continuous. They can be multivalued. Some concrete examples. Well, here's a Schrodinger operator with a potential where I form a potential which is just a sum over atomic. Think of atomic potential wells. I take maybe a square well or a negative Gaussian, and I place it concentrated about each of these lattice sites, and I sum over. That's an example of a honeycomb operator, minus Laplacian plus V for such a potential. And another way to get them is not by building them up atom by atom, but simply to interfere waves. So there's a technique called optical induction in nonlinear optics where one takes 3 plane waves and interferes them in a crystal. And so you could generate a pattern. And if you choose the wave numbers, the wave vectors of the plane waves appropriately, then you can generate a honeycomb pattern. And such optical induction is used to create periodic structures and used in many fields. But what these two examples have in common, these two examples have in common are the following properties. We call them honeycomb lattice, honeycomb potentials. They're periodic with respect to the triangular lattice. They're inversion symmetric. They're even as they commute with the parity operator. They're complex conjugate invariant. In other words, they're real valued. And then they have this rotational symmetry. If I define R, just ordinary R 2 pi over 3 to be a rotation of a vector in the plane by 120 degrees about the origin, then the potential V is invariant under this operation. And this is all with respect to the. I'm choosing an origin of coordinates so that with respect to which these symmetries hold, and I call that origin 0. So, okay. Now, suppose you take a honeycomb potential, for example, say this one over here, and I just plot the dispersion surfaces. Then you get something like this. This is an example where you plot the first 3 dispersion surfaces, and you see that in this case, the first 2 appear to touch at these points over here. And these points correspond to vertices of the Brouillon zone. And such conical points are called Dirac points. Very precisely, a Dirac point is an energy quasi-momentum pair, such that if you look at 2 adjacent dispersion surfaces, then they locally look like a right circular cone. There is this coefficient here which gives you the aperture of the cone, and that's called we'll call that the Dirac velocity, and it's something that you could compute from the band structure at this k value, k star. At the Dirac point, you see that the plus and minus branches degenerate, so there's a 2-fold degenerate eigenvalue corresponding to that quasi-momentum k star. So 2 spectral bands touch then. Those 2 neighboring spectral bands touch at a Dirac point. And a theorem that one can prove is that if you take any basically any honeycomb potential, say a generic honeycomb potential. Here I take by generic, for example, I could take this condition that the 1-1 Fourier coefficient not be 0. Then regardless of the size of lambda, for generic values of lambda, there are always Dirac points. There are always conical points somewhere in the band structure. And these occur at the vertices of the Brouin zone. For small lambda, they always appear. There are no exceptional values, but as lambda varies, as we'll see in just a second, you can have discrete values at which the existence of a Dirac point may fail. This is a perturbation analysis. This requires some global complex analysis and some functional analysis to study it for arbitrary contrast structures. And then there's work on what's called the strong binding regime of very deep potential wells. We have some results there for also 2D Maxwell along this line. Just a comment about why Dirac points occur at the vertices of the Brouin zone. What makes them special? And the key is that it's degeneracy of this extra degeneracy of eigenvalues arises due to an extra symmetry. Here's a lemma. Suppose I look at HK, right? HK is this honeycomb operator acting in the space L2K. That means it has, that's the K pseudoperiodic boundary conditions. And let me define this rotation operator that we saw earlier. Then the Hamiltonian commutes with this rotation operator if and only if K is a vertex. If and only if K is a vertex of the Brouin zone or translated by something in the dual lattice. Okay. So these, there's some commutation here. So this is a symmetry, right? And this symmetry only occurs at the vertices of the Brouin zone. And these, so therefore these vertices are called high symmetry quasi-momenta. Now, once you see that you have this commutation relation, it makes sense to look at the eigenvectors and eigenvalues of the rotation. And the eigenvalues are just the 3 cube roots of unity. And so this is a normal operator, so it decomposes into a direct sum, orthogonal sum of subspaces where corresponding to the eigenvalue 1 for the rotation, the eigenvalue tau, and the eigenvalue tau bar. And the tau and tau bar spaces are related by applying the symmetries of the honeycomb potential piece. So you can map one to another. So this two-dimensional eigenspace at the Dirac point is actually a subspace of this direct sum of these two, the tau and tau bar subspaces. So the picture is this: you have some. You have a conical. You have a conical behavior near the Dirac energy, and this degenerate eigenvalue over here sits in this space. This is just a local picture near one of the intersections. Now, I want to turn now for a moment to the case of high contrast electromagnetic structures in joint work with Maxence Cassier at Institut Fresnel. So here we're looking at a structure which is it's a dielectric structure, okay, and so we're looking at TE modes, and think of a structure which is made of dielectric pillars, okay, so you have high contrast inside the colored circles. It's the identical material inside the colors. The colors are just distinguishing the two sublattices, the A and the B sublattices, but you have some high contrast material inside the circles, and then it's maybe vacuum outside, okay. And so after a scaling, the formulation of this eigenvalue problem is given here in the case of transverse electric modes. It's a divergence form operator, and G here is the contrast parameter. Sigma is 1 in the bulk in the white region, and G in these colored circles. Okay. So that's the problem we look at, and we're interested in what happens at high contrast. I want to take G bigger and bigger, okay, and we want to ask that question. And what we show, and this is really very compressed without much detail, is that for sufficiently large G, this problem has Dirac points between the first two bands at the vertices of the Brouin zone for symmetry reasons, as I explained. And the proof of this, well, we're working now in a case where the potentials are discontinuous, right? The dielectric coefficients are discontinuous. It's just a two-valued function. And so we have to use a weak formulation of what's called a Schur complement Lyapunov-Schmidt reduction scheme that was developed in the context of Schrodinger equations. And then we also can say some global things about the band structures, namely that as you increase the contrast, and we'll focus on these pictures over here. Here is the K point. This K is a vertex of the Brouin zone. So as we go around a triangle in the Brouin zone where K is one of the vertices, you see there's always a Dirac point at K in all three of these. What distinguishes these three pictures is that the value of G, the contrast, is different. So this is smallest contrast, larger and largest. In this picture over here, the dispersion surfaces intersect in a Dirac point between I guess I'm not sure I used the right figure here. What I wanted to point out is that I guess if I had shown an earlier figure, for G sufficiently small, it's the first two bands that intersect in a Dirac point, and then as G increases, there's a transition through a threefold degeneracy, and then eventually what happens is it's the first two that intersect in the Dirac point, which is as stated over here. And another feature is that as the contrast increases, what you see is that there's a convergence of the bands onto this value over here labeled as delta 2, which is a Dirichlet eigenvalue of the isolated inclusion with zero boundary conditions. And depending on details, that convergence can be uniform. As is the case in the second band, you see it converges uniformly onto this limit, or in the first case, it's not uniform. You see here that near zero quasi-momentum, it's stuck at zero because of the divergence form character of the operator. Okay. Now, okay, I'll mention briefly. There's related work, rigorous and formal asymptotic. On the Schrodinger and Honeycomb problem, a lot of it perturbative, exact solutions, some results from a group representation perspective, linear and nonlinear honeycomb structures, work in granular crystals, elasticity, acoustics, and then there are other kinds of effective models than the tight binding ones that I'll talk about called quantum graphs, which have been studied. And then there's some of the analytical methods actually have relation to earlier work on general semi-classical ideas. Okay. Now, so I want to turn now to interface and energy transport. So we're going to start with the bulk Hamiltonian, focusing here on Schrodinger, and then we'll deform it in some way to an edge Hamiltonian. And what we want to do is we want to look at a Dirac point of this operator, a conical point in the band structure, and then investigate the nature of the spectrum and eigenmodes near the Dirac energy. What we'll see in all of these examples is that when we make this deformation, like create a sharp termination, there's going to be some kind of an effective Hamiltonian that describes the behavior near the Dirac energy. So the first deformation is a sharp termination, either along a zigzag or an armchair, and I'll state a theorem for zigzags. In this case, what is the edge Hamiltonian? Well, what I do is, instead of summing over the entire honeycomb structure, a sum over this object called H sharp, which is just a half plane of vertices. And I could create a half plane of vertices by terminating, say, along a zigzag or an armchair, or actually along any rational edge. So that's our model here. It's an operator acting on functions on all L2, the entire L2 of the whole plane, but it just so happens that the potential vanishes on one side of the structure. And the theorem that we have is that you get localization of edge states in this case. In this case over here, every indication is that there is no localization. So if you try to localize waves here, they'll propagate along and be concentrated along the boundary, where here they'll just simply diffract into the bulk. In the domain wall case, the Hamiltonians look something. I'm not going to write down the Hamiltonian just yet for this structure, but I'll just emphasize that there's a 1D analog, which is just a medium with a dislocation. So take a periodic function v of x and imagine doing a slow phase, an adiabatic phase shift across the structure, where asymptotically it's v of x plus delta at plus infinity and v of x minus delta at minus infinity. So that's a non-compact perturbation. That's a kind of phase shift across the structure. There is localization of edge modes in the corresponding Hamiltonian for these structures along arbitrary rational edges. Here it doesn't matter. Zigzag, armchair, or any rational edge will work for such domain wall structures. And then the third is we'll do the following. We'll take the we'll be looking at we'll look in the also at electromagnetic modes in 2D. And what we find is that if you deform the honeycomb structure, this is just a cartoon of the symmetries of 2D photonic material. Then what happens is, in a neighborhood of the Dirac energy, which sits over here, omega is omega d over here. And what happens is, what this perturbation does is, if you do the asymptotic analysis in the adiabatic regime, where it's a slow perturbation, then the effective model is a magnetic Dirac operator whose spectrum looks like that. So what happens is the deformation is, this is translation invariant in the vertical direction. So there is a ky, a parallel quasi-momentum. You still have some kind of translation invariance. And what happens is these energies are, instead of being a continuum, break into discrete energies, which are of infinite multiplicity now. These are so-called Landau levels, known in quantum mechanics. Okay, so those are the three edge situations or deformations I want to look at. And now to describe what's going on with these models, all right, we start with a Hamiltonian and we perturb it in some way by an edge. The bulk has all the symmetries, and then the edge just now has only, it loses a symmetry perpendicular to the edge, but it does preserve translation symmetry parallel to the edge. So I'm talking about, again, rational edges. You can imagine taking an irrational edge, and what I say does not apply to that situation. Then because of this translation invariance, you could view the operator as before in terms of the individual operators on these L2 spaces with pseudo-periodic boundary condition, where now the pseudo-periodic boundary condition is just with respect to this scalar parallel quasi-momentum. If I translate in parallel to the edge, then I kick out this block phase. But perpendicular to the edge, I'm looking for states that are going to be localized, right? So they'll be square integrable on a cylinder. So what the cylinder does is it makes things compact in the edge direction, where you get this pseudo periodicity, and it tells you that you get decay transverse to the edge. here we specify L2 decay, but we believe it's actually going to be exponential. So, okay, so the edge state eigenvalue problem is that for each k parallel, for each, we study this problem. And L2 eigenstates of this operator are guided, they're guided modes, right? They're localized about the edge, right? You got this edge direction, the edge, and we're looking at a state that's localized like that, and then it you know, propagates parallel to the edge. So this is what a block mode, or excuse me, what an edge mode looks like. It looks like it looks propagating parallel to the edge, and this is going to be periodic in x parallel, this amplitude over here, but it's going to be, say, exponentially localized in the direction perpendicular. Well, if you have a family of these edge modes, then what you could do is you can multiply by some density function, some weight, which is concentrated at a particular k parallel. Epsilon is that concentration parameter, and then you get a wave packet which moves with the group velocity given by the slope at the center parallel quasi-momentum and disperses on a time scale given by the curvature. So there's a lot of therefore there's a lot of important information bound up in these edge state curves, which I want to, which I'll show you some of those. Okay, so now that's the sort of general picture of how we think about the eigenvalue problems which characterize edge states, and we'll talk about them for sharp terminations, domain walls, and non-uniform strain. In the first case, so we're looking at the Honeycomb Schrödinger operator, but on a truncated lattice with a zigzag edge. And there, what plays a role in the limit as lambda gets very large, the so-called strong binding regime, is an effective Hamiltonian, which is called a tight binding operator. And basically, this is a difference operator on the lattice. It's telling you how, it tells you that, you know, if you think in terms of electrons, the electron hops to its nearest neighbor sites with a certain probability given by the coefficients. So that's the operator. This is an operator which acts on little L2 of a one-sided sequence. So you could think of it as a sequence where you zero out everything to the left of zero, and it has two amplitudes corresponding to the two sites per unit cell. And what we show here is a kind of spectral convergence, a convergence of the Green's functions, if you will, or a resolvent convergence. We show that if you center the operator about the Dirac energy, and then you divide by what's called the hopping coefficient, which in the quantum interpretation is it's the probability of tunneling between nearest neighbor sites, the probability of tunneling from here to there. So it's an explicit integral, which it's an emergent parameter, if you will. And it's bounded above and below by exponentials. Then in the limit, you could show that this continuum operator converges to this discrete operator up to simple conjugation, which makes the spaces correct. This is what the limiting operator spectrum looks like, actually, for each k parallel. So this limiting operator has translation invariance in one direction as well, right? That translation invariance is vertical, so there is a parallel quasi-momentum. And if I plot the spectrum for each value of k parallel, I get here a band, and then a gap, and then a band. And then if I change the energy between 2 pi over 3 to 4 pi over 3, there's a point eigenvalue. That's in it. Those are edge states. So these are exponentially localized states of the discrete problem. Here is the spectrum of the discrete problem. To get the spectrum, I just take the union of all over all k parallel, And so this flat band over here corresponds to an infinite multiplicity eigenvalue of this tight binding operator. In the continuum, this you don't get an eigenvalue of infinite multiplicity. What happens is this flat band is going to just deform to something nearby. You can see that numerically, like that. All right. In the domain wall case, well, there's a Hamiltonian. I'll just mention that we're not going to go into the details of the operators. They look, but there's a bulk part, and then there's a part which gives you this deformation way up here and way down here. So the operator is perfectly periodic above and below, but then there's this distortion that transitions through this tanh-like function from one side to the other. And there also, there is an asymptotic operator, there is a resolvent or Green's function convergence. Here, the effective operator is a one-dimensional Dirac operator, which looks like that. It has this domain wall function, this tanh-like function sitting in it. And you could derive it by multiple scale analysis. And this Dirac operator governs the transverse localization. It basically tells you the shape of the edge state transverse to the edge. Now, I mentioned the importance of edge state curves, and I wanted to show you some of these. So in the case where where we perturb by an edge which respects time reversal symmetry, then the edge state curves are symmetric. They have a symmetry. So in other words, if you make a wave packet out of these K parallels, you make a wave packet out of these, then they'll go in opposite direction. And then and notice that there are actually two classes of edge state curves or bifurcation diagrams, if you want to call them that. They're both symmetric and different for depending on the orientation of the edge. So there's a whole class of rational edges which give edge state curves that look like this, and then there's the other class, representative of which is the armchair, which gives you this kind of edge state curves. And in terms of topology, because of the time reversal symmetry, it turns out that these topological invariants, the so-called Chern number, is 0 in this case. So you do get edge states, but there's the algebraic count of the number of edge states is 0. There's a -1 with counts with this one, with every state here, and a +1 with the counter propagating one. So there's no net energy transfer because of this bidirectionality. In the case where you break time reversal symmetry, for example, with a magnetic field, then the edge state curves are unidirectional. And here also there's a difference. It depends on the orientation of the edge. Zigzag edges give you edge state curves that look like that, well separated, and armchair edges like that. And in this case, you do have a non-trivial topology. When you calculate these Chern numbers, you get that the difference is ±2, which tells you why you have these two curves. So the picture for edge state propagation in domain walls goes like this. Just to summarize, we start with the unperturbed bulk. It's a two-dimensional honeycomb structure with Dirac points like this, where two bands of spectrum touch. When you break with symmetry, with time reversal, like making it a gyromagnetic medium, then what happens is you gap the system, you gap near the Dirac point. This cone becomes two paraboloids sitting nearby with a spectral gap. And now what you do is take two such structures, which are topologically distinct. In other words, their Chern numbers are different. Then what happens is this gap over here, I mean, the continuous spectrum stays the same, but this gap due to this difference of Chern numbers, fills with modes. And if you ask, what is the nature of those modes? Well, those are edge modes, which propagate unidirectionally. And they can be quantified by, you can quantify the energy transport, in this case, by the difference of Chern numbers, which is 2. And I mentioned a proof of this for such models by Alexei Giroux recently. Okay, now let me get to the third example, and that is pseudomagnetism in strained photonic crystals. So when we say strained photonic crystals, we're not taking photonic crystal really and straining it. What we do is we figure out what is the shape, what is the deformation that gives rise to a certain effect, and then that gets etched into an array of honeycomb structures. So it's, well, although I've drawn it as a mechanical deformation, it really is something that you simply write into a slab of material. So, okay, and we want to understand how, if you look near the Dirac energy, you get these distinct Landau levels. And I want to point out that in our derivation, it's a general derivation which really makes use of symmetry properties. This phenomena is known in graphene and is derived in the context of graphene from tight binding models. But in photonics, as we know, many situations, although are not at all tight binding, nevertheless, we have the effect. So our derivation is a more general one, applicable to photonics and other areas. Just mention that, well, this is done by a kind of multiple scale analysis. We start with some deformation. Capital T defines the deformation of the structure. There's a parameter kappa, which for us, which is the scale of the deformation, which is, and that 1 over kappa is kappa is an adiabatic parameter, so 1 over kappa, the scale of the deformation is much larger than the lattice constant. And we derive a multiple scale expansion whose effective Hamiltonian is a magnetic Dirac operator. And the nice thing is that the effective magnetic potential, A effective, and there's an effective electric potential, those are all explicitly computable in terms of the deformation. You give me a deformation, and I have formulas for A effective and W effective, and there are no free parameters. Here is what the numerics show. This is the Dirac point of the undeformed structure, and now here you see the emergence of these flattish energy levels. They're not exactly flat, but if you take our multiple scale analysis and you figure out what is the energy spacings that come from these flat Landau looking levels, then we get very good agreement with a full numerical simulation for the 2D structure. Full Maxwell simulation. Okay, so I'll start wrapping things up. So we are looking at waves and honeycomb structures and their deformations. Dirac points are conical points in the band structure. When breaking symmetry, either sharp termination or domain walls or external fields, magnetic fields, the conical point is gapped. And then interfacing different structures can lead to essentially a new material with conducting properties along the interface, and that in these topologically non-trivial cases, there's a robustness which is explained in terms of a topological index. We elucidate these phenomena by PDE and asymptotic methods through comparing the continuum operator to some asymptotic model. It could be a discrete tight binding model. It could be a magnetic Dirac operator or some kind of an effective Dirac operator that is non-magnetic. I want to mention very recent work on strongly magnetic systems. So coming back to this kind of archetypal example in the field, this is the Hamiltonian for the integer quantum Hall effect, but you could think of it as really a surrogate for problems with maybe electromagnetic problems with a magnetic, some kind of magnetic effect. I want to take the crystal again. There'll be some atomic potential well, which say sits at the lattice sites of a crystal, and now here I'm summing over discrete points, and I could allow that set of discrete points to be disordered. All I need is that the points don't accumulate. So imagine some kind of random speckle of points, infinite points in the plane. There's no translation invariance, no block theory, but we understand how to take the limit in this Green's function, resolve in sense, and go from an operator, the continuum operator, to a discrete operator on little L2 of the discrete set. And because we're working in a situation of where things are magnetic, what we get is a magnetic type binding operator whose coefficients are complex. There's a very important example that plays a role in condensed matter physics called the Harper model, which corresponds to taking G equal to just the integer lattice C2. And the Harper model has very, very exotic spectrum. Depending on how you pick your coupling parameters, how you go to infinity, essentially, or you can arrange for different, what amounts to is a different magnetic flux per unit cell. Remember, the magnetic field is coming through the honeycomb, so if you can calculate the integral of A dot dl around a circuit of a single cell, and that defines a magnetic flux. And depending on the value of the magnetic flux, you can get basically Cantor-like spectrum. So there's something called the Hofstadter butterfly, which describes the spectrum of this asymptotic model. And we're able to capture such models for the continuum through this procedure. And then the second is that we've recently proved that the topological indices associated with H lambda and those of the tight binding magnetic problem are actually equal. And so this is in typical physics papers, they'll work with discrete tight binding models, but what this does is it gives some kind of justification for this ubiquitous use of tight binding models in topological physics. And then I'll just conclude with just a couple of words about directions and open problems. There's a very interesting question about metastable states. In typical physical problems, you don't have the Dirac points are not perhaps so clean because dispersion surfaces can fold over if you're at lower contrast. So for example, here is a Dirac point at K, here's my energy ED, but there might be other modes far away in K space to which you can potentially couple. And this would lead to slow leakage into the bulk. It would be very interesting to have a good theory of that kind of momentum space tunneling. And does it in any way depend on whether there is non-trivial topology? That would be interesting to understand. There's we're interested in problems with nonlinearity, say for the Gross-Pitaevsky equation, but also in recently there's interesting work by Alu, Haddad, Vitelli, Honikayev, who look at metamaterials which are comprised of coupled arrays of electrical circuits, nonlinear electrical circuits that appear to exhibit interesting topological properties. And so with the student Yu Li, I'm currently working on that. More questions on disordered crystals. And then there are multi-layer structures like bilayer graphene and twisted bilayer graphene that has received a lot of attention. And I should mention that Alu and collaborators have actually studied metamaterial structures with a lot of the same effects that you see in the condensed matter problem. So with that, I'll stop.
Thank you very much, Michael, for these great talks. So I guess we will have a lot of questions because there were various aspects. So perhaps Muammer Kadi can start with a question.